Thanks everybody for attending my talk. Today I'm going to talk about downfall attacks exploiting speculative data gathering. Well, let's talk about what this gather instruction is and how it's going to leak some data. So this gather instruction is introduced in x86 about like 15 years ago as part of the AVX2 extension, and it's supposed to speed up accessing scattered data in memory. We have a bunch of different instructions for these, for different data type, different vector sizes, and we can also use this instruction as part of Intel intrinsics library if we are writing some C code and we want to directly call this instruction. And this instruction is used everywhere in a lot of places. I just did some Google search on GitHub and things like that, and it's used in a lot of places like database, cryptography, scientific computing, video encoding, AI inference, and so on. So essentially, anybody who want to do highly intense like data processing, it can use this instruction to get some benefit for computation. How does this instruction work? Imagine I'm a software developer and I want to write some algorithm that accesses non-contiguous or scattered data in memory. I have a bunch of indexes. Naturally, if I want to access this data, I will write a for loop, access each index, and then here in this particular case, I only want to do computation for every other index, so I do that if statement. This generally executes not so fast. There are maybe some speculative execution and things like that, but still, it would not be as fast as we want because it's a sequential code. But we can rewrite this code with the AVX extension, and we have this gather instruction. It accepts a lookup table, an index, and a mask vector register, and that mask vector register does the if statement, and then we can get the data and do another vector operation to perform the computation. And this looks like something like this. We have a bunch of scattered data. The CPU uses indexes to find the data, and based on that mask, is going to put them into the software register. But underneath, the CPU can do a lot of interesting things to make this instruction a lot faster. Some of these things that are interesting here for this talk is like, for example, reusing the same data from the same cache line. Imagine some of those indexes are hitting the same cache line. We don't want to just keep requesting the memory to give us the same cache line again and again. Or sometimes when we are executing this instruction can execute up to 16 different memory operations, and we may interrupt this instruction, and the CPU can preserve the partial execution, and when the interrupt resumes, continue accessing the rest of the data. And in the meantime, the CPU can also forward data that is available to the next instruction, so it doesn't have to wait for all the 16 or 8 memory accesses to complete before continuing the execution. So essentially, gather can allocate some hardware registers or hardware buffers and forward data speculatively. And this would look more like something like this. We have a bunch of hardware, physical registers, physical buffers, and the CPU is going to allocate one of these buffers and then eventually bring the data to the physical register and also map it to the software. Wait a minute, shared buffers forwarding data speculatively. This is fast, but what can go wrong based on prior experience we have with this kind of optimizations? So in 2018, meltdown attack was discovered, and the idea was that the attacker could leak data from the data cache. And Intel ultimately claimed that they fixed this vulnerability in the 9th generation Coffee Lake CPU. And then there were a lot of different researchers, including myself. We showed that this mitigation is broken because you can still leak data from these different microarchitectural buffers inside the CPU. And Intel again claimed that by 10th generation CPUs, they have finally fixed this issue in the hardware. And there were some glitches when they deployed this fix because some of the parts that they sold, they still didn't have the mitigation properly enabled. But finally, by the middle of 2020, everybody was fully confident that we have fixed this problem forever. And one thing these attacks had in common is that there are these CPU buffers that keep data from shared users. And when we have an attacker that accesses a memory that hit an exception or microcode ST, something that we saw earlier in a prior talk, then this is gonna leak from these different microarchitectural buffers. Meltdown leaked from the L1 data cache, Fallout leaked from the store buffer, zombie load and readle from the line field buffer, and also readle from the load buffer. In this talk, I'm going to talk about the gather instruction leaking from that buffer in the middle, which is the vector register file. The attack is called gather data sampling. The attack is pretty simple. Once you find this vulnerability, you realize that you can simply exploit this. So imagine we have a victim that executes a thread on this CPU, and the victim does a bunch of vector operations populating the register file with some data. Now, the attacker performs a few steps. The first thing the attacker can do is to do a bunch of cache flushes and cache misses to put the CPU in a speculative state. This can also happen with other operations, for example, with a page fault or other sort of things that put the CPU in a speculative state. Now, the second thing an attacker do is just execute the gather instruction. And that's just executing the gather instruction. The gather instruction doesn't even need to have a fault or anything special. And then we encode the output of the gather instruction to the cache and scan the cache, which the last two steps is very similar to the original meltdown and macroarchitectural data sampling attacks. OK, I'm going to try to run this attack. So here I have a proof of concept that run this attack with like 8 CPU threads that the user just spawn and randomly spy on some string values. And here you can see some interesting stuff are showing up. And if I, as another user, I do a bunch of, let's say, printf here, printing the password, we see more strings are going to pop out. All right. So this is how this attack works. One thing that was interesting for me is what kind of instructions are affected by this particular vulnerability. So I developed a simple tool to automatically test all sorts of different memory operations, which basically extract all memory operations from the LLVM assembler test case and execute each of them with a known data pattern. And at the same time, we're going to execute the gather data sampling on the same core and see if we leak from any of those instructions. The highlight of this experiment was that all SIMD instructions that load from memory leaks. That includes extensions like ASNI and SHA-NI that are developed to execute cryptography fast. Also, there is this important instruction for copying data fast, which is called repmove, that also leaks. And also some special instructions to restore the register context that they also leak. And apparently these last two, they are instructions that are microcoded to execute in a SIMD fashion. The other important thing also is how much data we can leak every time we speculatively execute the gather instruction. So I came up with this experiment that this time I'm going to encode all the 32 bytes of a vector instruction to the cache and see how many of them are there. And on the sibling thread, I execute a bunch of remove instruction to populate the register file with some strings. The highlight of this experiment on the 11th generation core CPU was that we could leak up to 22 bytes strings. And most of the strings are something like 17 to 22 bytes. And if we compare this to the previous macroarchitectural data sampling attack, this is a lot of data that we leak every time we execute this instruction, because the previous attack could only leak maybe 3 or 4 bytes every time. Another important thing is the data pattern that we can leak from the register file, because the register file doesn't necessarily map to the gather instruction the same way that all the other instructions map. To do this experiment, I loaded different data pattern, different cache into the register file, and then execute the gather data sampling attack with different vector encodings, which supports 32-bit and 64-bit, and also permuting the output of the gather instruction before encoding it to the cache to see what part of the vector registers I can leak. The highlight of this experiment was that we could leak contiguous data with 4 or 8 byte patterns. As we see in those tables, the left one is the 4 byte pattern, the 8 byte is the right one is the 8 byte pattern. So they kind of overlap and we leak from them. But ultimately, we can leak an entire SIMD register because we can use the vperm instruction to permute the output of that leakage every time. So every time we execute gather, we can target a different part of that register. Now I'm going to talk about how we can use this attack to steal encryption keys. The attack I developed, and I wrote it to the paper. Also, there's a demo and video and everything on the website. The idea is that we have a victim encrypting some random data with OpenSSL command line tool, something like that, the off-the-shelf OpenSSL command line. And we use the same key, of course, when we execute this command, and it encrypts a bunch of block of data. When we do this, the AES algorithm naturally expands this master key to a bunch of round keys. And then the AES-NI, for every block of encryption, is going to repeatedly load these round keys to the register file. And we obviously know that one of these round keys is the master key. So this is the master key, and supposedly this is in the vector register file. And we have a bunch of round keys too. We don't necessarily care about them here that much. And then we also have a bunch of random data because we are encrypting the random data. So those random data are going to be also loaded to the vector register file. One observation was that when we do this, the round keys are going to be leaked with a higher frequency than everything else because they are repeated for every block of encryption. So I developed this attack that the attacker execute the gather data sampling to leak 8 bytes at a time, the maximum size of contiguous chunks we can leak. And then we keep chunks that have a high frequency and uniform distribution because that's how the AES key looks like. They have a uniform distribution, and they also happen with high frequency. And we combine these chunks, these 8-byte chunks, to create AES round keys. And finally, if we search through those round keys to see which one is the correct key. The attack complexity for this was 8-bit for AES 128-bit and 12-bit for 256-bit AES. And this looks like something like this. Imagine we have 2 round keys in the register file, and the same apply if we have 10 rounds key, which is the AES 128-bit. We leak the first 8-byte chunks, then the second 8-byte chunks, then we mix and match them, and we have 4 candidates, and then we brute force that. Let's look at this in a live demo. Hopefully, it's going to work out. So here, we have a victim that is logged into this computer. Maybe I should make it bigger. And then we have the attacker that's also logged into this computer. All right. So the victim is going to run this script that just runs OpenSSL command that I mentioned to you for 10 seconds. And then here, we run this attack. It's going to first sample for 5 seconds the first 8 bytes, a bunch of candidates. The second 8 bytes, a bunch of candidates. And then it brute force the full matching candidates. This is the stolen key, and this stolen key matches this original key. So there are also other interesting attacks in the paper. For example, I showed that you can also steal arbitrary data from other applications, in particular showcasing on Linux kernel with help of some memcopy gadgets that are very common in all sorts of applications. You can also steal the sealing key from Intel SGX to compromise all secure enclaves, because once you steal the sealing key, the remote attestation is compromised, and you cannot really trust a remote party if they are running the correct SGX. And there's also another attack technique called gather value injection, which is very analogous to MBS and LVI. Here we have GDS and GVI. So what are we going to do about this mess? Historically, when this kind of vulnerabilities showed up, people proposed something to flush microarchitectural buffers. But right now, Intel has not decided to do that, so we don't have any instruction sequence to flush vector register file. I would highly not recommend doing that in software, because I tried. It's expensive and really unreliable. So you don't really know if you are mitigating it. This also doesn't mitigate against Intel hyperthreading, so you can still attack through hyperthreading and not good. So the mitigation Intel has proposed is a microcode update. They claim that only gather leaks from this register file. So they modified the gather in the microcode to not forward data speculatively anymore. And this has like something up to 50% overhead for workloads that use this instruction, and if this instruction is in the critical path. And the other important thing is, after these fixes are deployed everywhere, everybody need to make sure that they check the SGX remote attestation correctly, so they are running on the latest firmware. But unfortunately, Intel has not recovered the trusted computing base yet. So for another month, everybody can go just compromise SGX, and there is no security, basically. In conclusion, we see that a single hardware vulnerability undermines all sorts of security boundaries, OS, VMM, SGX, and it affects billions of computers, laptops, desktops, servers. And these attacks are practical and easy to exploit, which Intel doesn't agree, but that's the proof of concept. And despite all these efforts for 5 years, CPUs still expose user data. In fact, they expose a lot more because of the size of the register file. And we have these complex optimizations in CPUs that introduce new vulnerabilities. And all these tests that we do pre-silicon, post-silicon, they still have a lot of gaps because clearly we could not have captured this vulnerability with automated tests before. So please ask your OEM and providers to provide you microcode fixes. With that, I would like to conclude my talk. You can learn more about it on downfall.page.